What's up, everybody? It's Short Transformation here again to talk to you about symmetry. And I love symmetry, especially with my two buys right here. Yeah!
First thing we're talking about is symmetry. That's when a reflection, translation, or rotation of a plane figure maps the figure onto itself, leaving the figure unchanged. So we have a couple examples down here of two-dimensional figures that have symmetry. And you can see why they would have symmetry. This one is a little more apparent than this one. Here, this would have symmetry if you were to cut it in half, this way or this way. It would even have symmetry if you were to cut it in half diagonally. So this has several different forms of line symmetry, which we'll talk about in a second. This figure right here would have something called rotational symmetry because you could turn it and get the same figure. We'll talk more about these types of symmetries in a second. Next thing we're talking about is line symmetry. That's when a figure can be mapped onto itself by a reflection in a line. So here are several examples of figures with line symmetry. It's just when you are able to draw a line through a figure and both sides are congruent. Here you can see I could draw a line straight down the middle of this photograph and both sides of the photograph are congruent. Each side could be mapped on to the other by a reflection in the line that I draw. Same thing with these figures over here. Now, rotational symmetry is when a figure can be mapped onto itself by a rotation between 0 degrees and 360 degrees on a point. So here you can see two examples of figures with rotational symmetry, meaning that I could pick a central point and then rotate this figure, and I would get the exact same shape before I got all the way back around with a 360-degree rotation. Same thing here. I could find a central point, rotate this figure, and I would get the exact same figure without having to go all the way back to the original figure at a 360-degree rotation. Plane symmetry is when the three-dimensional figure can be mapped onto itself by a reflection in a plane. Okay, so plane symmetry is just like line symmetry, except line symmetry is two-dimensional, whereas plane symmetry is for three-dimensional figures. So if I were to chop a box like this in half right down the middle, as you can see, this figure would have plane symmetry because it's exactly the same on this side that it is on this side if I were to cut it in half with a plane. Same thing over here, these cubes. If I were to cut them with these given planes in orange, they would be the same on either side, meaning that they would have plane symmetry. Axis symmetry is when a three-dimensional figure can be mapped onto itself by a 0 degree to 360 degree rotation in a line. So just like line symmetry is two-dimensional and plane symmetry is three-dimensional, rotational symmetry is two-dimensional, whereas axis symmetry is three-dimensional. So if we were to look at this football down here and kind of disregard the laces, I could insert a pole through the middle of that football and spin the pole so that the ball would then rotate around that pole. And the ball would be the same while I was rotating it, right? There would be points where the ball would be exactly the same as it was in the beginning, disregarding the laces. Same thing if I were to stick a spike straight down the middle of this ball, and if I were to rotate it 180 degrees, it would be the exact same that it was at the beginning. Then I would rotate it 180 degrees more, and we would get back to the original figure. So that's when a figure has axis symmetry.
You better believe we're doing examples now.
Now, example 1 is to state whether the figure appears to have line symmetry. If it does, draw all lines of symmetry on the figure. So, this is asking you, is there a line of reflection that you can draw where you can get the figure then to map onto itself with a reflection? An easier way of looking at it is there a line that you can draw where the figure would be the same on both sides of the line? The one place that it seems like you could draw it would be right here, but this side appears to be shorter than this side. So this figure would actually have no line symmetry. Part B, can you draw some line of reflection through this figure where you could get the figure to map onto itself with a reflection? Yeah, there's actually multiple different ways you could draw a line. You could draw one here. If you were to draw a line here, it would cut this figure in half where it would be the exact same on both sides, meaning you could map the figure onto itself with a reflection. Same thing here. If you were to draw a line down the middle, each side would be congruent, meaning that you could map this figure onto itself with a reflection. Same thing if you were to draw a line diagonally here and here. Each of those would cut the figure exactly in half where the figure could map onto itself with a reflection in that line. So yes, this figure does have line symmetry.
You better try this right now.
Okay, doing the same thing here. So in this figure, is there a line of reflection that you can draw where one side would be congruent to the other side, meaning that you could get the figure to map onto itself with a reflection in that line? Yeah, you could draw a line through the figure right here. This would cut the figure exactly in half, with one side being congruent to the other and allowing you to map the figure onto itself with a reflection in this line. Same thing with this line right here. This would be a line of reflection that cuts the figure exactly in half, with one side being congruent to the other. And same thing if you were to draw a line straight down the middle, that would do the same thing. So yes, this figure does have line symmetry. Here, is there a line of reflection that you could draw where you could get the figure to be the exact same on one side that it is on the other? That would allow you to map the figure onto itself with a reflection. No, even if you were to draw a line like right here and slant it a little bit, no, you couldn't like reflect this onto itself because these are too slanted. So you would say that this figure does not have any line symmetry. Example 2 says state whether the figure has rotational symmetry. If it does, locate the center of symmetry and state the order and magnitude of symmetry. So we are trying to determine if this figure has rotational symmetry, meaning can we rotate this figure around a point and get the exact same figure with the exact same orientation without going all the way around a 360-degree rotation? Yeah, if I were to put a point in the center of this figure and then rotate it, I could get to the same figure if I were to rotate that 180 degrees. So yes, this does have rotational symmetry. We then have to state the order and magnitude of symmetry. So what is the order of symmetry? The order of symmetry is just how many times the figure maps onto itself from 0 degrees to 360 degrees. So here's how this works. We're going to figure out how many times can we spin this given shape and get the exact same shape from 0 degrees to 360 degrees. If you look at this figure closely, you can see that these two sides would actually be shorter than these two sides. So we can't just spin this 90 degrees and get the same shape. We actually have to spin it 180 degrees to get the exact same shape. And then we would spin it 180 degrees again to get it back to normal. So this figure would map onto itself one time after 180 degrees and then back to itself with a 360-degree rotation. So we would actually count that as an order of symmetry of 2. Now, think about it this way. If a figure does not have rotational symmetry, its order of symmetry is just going to be 1. That means you could spin it around and it'll only map onto itself after you get back to 360 degrees. This one maps onto itself at 180 and 360. So we count that as an order of symmetry of 2. The magnitude of symmetry is actually really easy. It's just taking 360 degrees and dividing it by the order. So our order of symmetry is 2. So 360 degrees divided by 2 would be 180 degrees. And that just tells you how many degrees it'll take to rotate this figure around this given point to get it to be the exact same figure, to map onto itself.
Time for you to try.
Okay, we're doing the same thing here. So, is there a place I could put a point and then rotate this figure about that point to get the exact same figure to map this figure onto itself? Yeah, if I were to put a central point right here and then rotate this figure around that point, I could get this figure to map onto itself at least 1, 2, and then 3 times if you got all the way back to 360 degrees. So yes, this does have rotational symmetry. And again, we want to find the order and magnitude of symmetry. The order of symmetry, how many times does the figure map onto itself from 0 degrees to 360 degrees? So when you have a regular polygon like this, it's easy just to look at one vertex and then rotate and see when that vertex hits another vertex. So if I were to rotate here, yeah, that's 1 time, it's the same figure. Boom, that's 2 times it's the same figure. And then we're back to the same figure after a 360-degree rotation. So that would be 1, 2, and then 3, because we count that 360-degree rotation, so that would be a order of symmetry of 3. And then we find the magnitude of symmetry by taking 360 degrees and dividing it by the order. So 360 divided by 3 is actually going to give you 120 degrees. That's how many degrees it'll take to rotate around this point in order to get this figure to map onto itself to be the same figure. Part B, doing the same thing. So first, is there a point I can put in here where I could rotate this figure about that point and then get the exact same figure without getting all the way around? Yeah, if I were to put a point right here, since this is a square, I could rotate around that point, and there's going to be at least 4 times that I get the exact same figure. So we say, yes, this figure does have rotational symmetry. I then am going to state the order of symmetry, which is how many times the figure maps onto itself from 0 degrees to 360 degrees. So again, since we have a regular polygon here, we just look at a vertex and then see when I rotate this figure, how many times does it hit another vertex to be the same. So we go 1 time, 2 times, 3 times, and then 4 times would get the figure to map back onto itself if you were to rotate that all the way around. So this would have an order of symmetry of 4, meaning that if I were to find the magnitude of symmetry, which is just taking 360 degrees, dividing it by the order, I would get a magnitude of symmetry of 90 degrees, meaning that I could rotate this figure around this point 90 degrees, and it would map onto itself and get the exact same figure. Now, example 3 says, state whether the figure has plane symmetry, axis symmetry, both, or neither. So, this figure right here, this is a cube. Does it have plane symmetry? Is there somewhere where I could chop this in half with a plane and get the exact same shape on both sides? Yeah, you could chop it down the middle here, you chop it down the middle here, you could chop it diagonally, and yes, it would have plane symmetry. Would it have axis symmetry? Can you stick a pole through it and then rotate it and get the same figure as you're rotating around? Yeah, you could stick a pole down the middle here, through here, down the middle here, and as you rotate it, it would map onto itself before you got all the way around 360 degrees. So this does have both plane symmetry and axis symmetry. Let's look at B. This figure right here. Is there some way you could chop this where it would be the exact same on both sides? Actually, yeah, if you were to cut it down the middle right here, it would be the exact same on both sides, right? So it would have plane symmetry. Now, axis symmetry, is there a way you could stick a pole down the middle of it and then rotate it around and get the exact same figure? No. Because of this little guy right here, there's nowhere where you could just put a pole down the middle and it would be the same before you got all the way back around to a 360 degree rotation. So this figure right here would just have plane symmetry.
Stop it! You try!
Okay, so first, let's determine, does this have plane symmetry? Is there somewhere where you could chop this figure in half and get the same figure on both sides? Yes, you could chop it down the middle here, here, or here, and you would get the exact same figure on both sides. So it does have plane symmetry. Does it have axis symmetry? Is there somewhere you could stick a pole through the middle and then rotate it around, and it'll be the same figure before you get all the way around 360 degrees? Yeah, if I were to stick a pole through the middle of this triangle right here and have it go through the middle of the triangle in the back, I could rotate it and it would be the same 1, 2, and then back to itself after 3 rotations of 120 degrees. So yes, this does have plane symmetry and axis symmetry, so it has both. Here, does this have plane symmetry? Is there somewhere where I could chop it down the middle? It'd be the same on both sides? Yeah, you could chop it down the middle like this, or you could chop it down the middle like this, and you would get the exact same shape on both sides, so it has plane symmetry. Does it have axis symmetry? Can I stick a pole through the middle of it and then rotate it around? It'll be the same before I get all the way back around 360 degrees? Yeah, if I were to stick a pole straight through the middle, I could rotate it around 180 degrees and it'd be the same figure. So this figure has both plane symmetry and axis symmetry.